You harvest a beautiful, perfectly ripe piece of fruit, but the moment it comes off the branch, a clock starts ticking. Within days, the flesh softens, the colors fade, and it collapses into mush. That decay is driven by biology. Naturally occurring enzymes begin breaking the food down from the inside out, while ambient temperatures awaken microscopic bacteria and fungi that feed on protein-rich foods. Look closely at the thermometer graphic. The range between 5 and 60 degrees Celsius is known as the danger zone. In this window, those sluggish microbes shift into overdrive, swarming and consuming edible supplies at an exponential rate. Bypassing that biological clock was the only way early human societies could store enough calories to survive a long winter or a failed harvest. For thousands of years, our counterattacks were simple. We drained the moisture out of grains by leaving them in the sun, or we dropped vegetables into acidic saltwater to pickle them, creating harsh environments where microbes couldn't survive. In 1810, Nicolas Appert figured out how to seal food in airtight containers and boil them. This method, canning, allowed preservation to scale up onto massive assembly lines, turning a daily household chore into an industrial system. A few decades later, Louis Pasteur proved exactly why these heating methods worked. He discovered that applying controlled, specific heat actively destroyed the microscopic organisms responsible for both spoilage and disease. That principle, pasteurization, was quickly applied to highly sensitive liquids like milk. By monitoring exact temperatures in holding tanks, suppliers could guarantee the microbiological safety of their product before it ever reached a city market. With these techniques, eating was no longer strictly dictated by unpredictable seasons and local harvests. Food became a continuous, reliable supply chain. Today, we live in an agro-surplus society, and our expectations are complex. We don't just want food that lasts the winter. We want groceries that are organic, packed with fortified vitamins, and capable of sitting on a shelf for months without losing flavor. Delivering all of that requires food science, the rigorous academic study of the exact chemical, physical, and biological composition of raw agricultural ingredients. Once scientists understand a crop's precise makeup, they apply food processing. These are the specific physical methods used to convert a freshly harvested plant or animal into an edible product. Combine those disciplines, and you get food technology. It is the legal, scientific, and socioeconomic system that manufactures those items safely, consistently, and at a massive global scale. This control panel diagram illustrates the core of that technology. Operators adjust 5 distinct dials to suppress biological threats: the application of heat, the removal of moisture, the lowering of temperature, the reduction of pH, and the control of oxygen. Turn those variables in the correct combination, and you have the blueprint to engineer almost any edible item imaginable. You can see the results of those 5 interventions here at the checkout counter. The sheer variety of packaging represents highly specific classes of processing. Class 1 covers minimally processed foods like pre-sliced apples, while Class 2 covers preserved foods like frozen peas. Both use temperature control to keep the original character of the fresh plant intact. Class 3 features manufactured goods like pickles, and Class 4 brings in formulated foods like bread and ice cream. Here, raw ingredients are crushed, cooked, or blended to create entirely new, shelf-stable items. Class 5 contains the derivatives. Industrial facilities use chemical and physical methods to extract pure components directly from crops, pulling pure sugar from cane or pure oil from seeds. Finally, Class 6 yields functional foods like probiotic yogurt, and Class 7 produces medical foods like low-sodium salts, items engineered to target specific biological traits or manage dietary diseases. Processed food is not a single monolith. It is a highly tuned spectrum ranging from simple refrigeration to advanced biological engineering. A highly specialized human workforce oversees the transition from raw material to marketable product, monitoring every stage of the pipeline to ensure the system remains safe. This flowchart maps out HACCP, Hazard Analysis and Critical Control Point. It's a strict testing protocol where inspectors intercept contaminants at designated stages long before a product is finished. But safety is only half the equation. Technologists also rely on precise sensory evaluation and recipe development to ensure that a batch of curry cooked in a 1,000-gallon vat actually tastes good. A mass-produced item fails if it makes people sick, and it fails if no one wants to eat it. Human oversight connects the raw laboratory science to your dinner plate. That same human element drives the next wave of research and development. Technologists engineer complex solutions to modern health crises, developing specially treated proteins that replicate the texture of fat, or designing low-calorie artificial sweeteners to combat diabetes. We are pushing our dietary limits far beyond the grocery aisle, utilizing specialized vacuum-sealed pouches and precise moisture control to safely feed our astronauts in the extreme environment of orbital space. Professional opportunities in this expanding field range from managing international corporate research to launching small-scale, localized dehydration ventures. By constantly adjusting the variables of biological decay, technologists function as the critical architects of the global supply chain, transforming raw agricultural yields into a consistent, year-round food supply.